Welcome to the second session on heat transfer. In the last session, we discussed what is meant by heat transfer, what is the importance of heat transfer, and what are the modes, the three different modes in which the heat transfer takes place. In the last class, we studied that heat transfer is the transmission of energy. Heat is also one of the form of energy, and the heat transfer, the transfer of heat, is defined as the transmission of energy from one region to the another region as a result of temperature gradient. Heat transfer is defined as the transmission of energy from one region to the another region, from one place to the another place as a result of temperature difference. And in the first law, in the thermodynamics, we studied that if the heat enters into the system, it is said to be positive, and if the heat or the energy leaves the system, it is said to be negative. And we studied what is the importance of heat transfer, what is the need of heat transfer, what is the need of to study the heat transfer. The concept of heat transfer is very useful in the design of heat exchangers such as boilers, condensers, evaporators, radiators, not only in the mechanical devices but also in the electric and electronic devices such as computers, refrigerators. Also, the heat dissipation, the concept of heat transfer is very useful because the cooling is required, it is necessary in every part, whether it is an electric component, whether it is an electronic component or a mechanical component. Therefore, the concept of heat transfer is not limited only to the mechanical department, but it is a vast subject which is applicable everywhere. Okay, then we studied what is meant by what are the modes, the ways in which the heat transfer takes place: conduction, convection, and radiation. We studied that the conduction is the transfer of heat from one part of the same substance to another part of the same substance, or from one part of the substance to the another substance which are in physical contact. In conduction, there is no appreciable displacement of the molecules. Although there is a displacement of the molecules, it is at the microscopic level. Here the transfer of heat or the transfer of energy takes place because of the physical contact. There is no appreciable displacement of the molecules. Conduction is the transfer of heat from one part of a substance to another part of the same substance, or it may also take place from one substance to another which are in physical contact. And here the displacement of the molecules is very negligible, without appreciable displacement of the molecules which forms that substance. Therefore, conduction is a microscopic phenomenon, and it occurs in all the mediums, whether it is solid, liquid, or the gaseous. The conduction takes place in all the mediums, but in the solids, the most of the heat, it is the only mode of heat transfer, because in solids there is no movement of the molecules. It takes place at a smaller level, at a microscopic level. Therefore, conduction is the only mode of heat transfer in solids. And we discussed what is meant by convection. Convection is the mode of heat transfer which mainly takes place due to the movement of the molecules. In solids and in liquids and gases, not in solids, in liquids and gases, even though the solid, liquids and gases are in the static condition, even when they are at the state of rest, the molecules of the liquids and gases are not confined to one position, but they continuously change their position. They are in a state of motion always. and the transfer of heat takes place due to this motion of the molecules. The transfer of heat from one region to the another due to such macroscopic of motion of the molecules in a liquid or gas is called heat transfer by convection. Convection is the mode of heat transfer where the energy transfer from one region to the another region takes place due to macroscopic motion of the molecules. Okay, again the convection is classified. We studied that in the last class. We studied that the convection is again classified into two categories: forced convection and free convection, or it is also called natural convection. Forced convection is the mode of heat transfer where the motion of the molecules is caused by an external source or the external agency, such as pump or the blower. Here the circulation of the water molecules or the liquid molecules or the gaseous molecules doesn't take place by its own in the forced convection. Here the fluid motion, the fluid particles are made to flow or made to move from one region to the another region by an external agency such as a pump or a blower. When the heat transfer takes place with the help of a pump or a blower, that type of convection is called the forced convection. When the fluid motion caused by an external agency such as a pump or a blower, the situation is said to be forced convection. The second one is free or natural convection. When there is no external agency, when there is no pump or the blower, but the fluid motion occurs due to the density variation, which is mainly caused by the temperature difference, the situation is known as the natural convection. Here the motion of the particles, motion of the fluid particles takes place due to the density difference. What happens? The fluid particles which are very near to the heating source gets heated first, and when the fluid particles which are near to the heating source gets heated, they start moving away from each other. The density of the fluid decreases, and the fluid particles which are far away from the heat source having higher densities. Due to this density variation, the fluid particles moves from their position. The motion of the fluid particles takes place. Such convection, such transfer of heat is called free convection or natural convection. Here no blowers, no pump is used for the motion of the fluid particles. The third mode of heat transfer is radiation. In the conduction, what happens? The transfer of heat takes place because of physical contact of the particles. In the convection, due to the motion of the fluid particles. But in radiation, no particle is required. The transfer of heat or the exchange of heat takes place purely by electromagnetic radiation in the form of electromagnetic waves. The best example is the energy exchange between the sun and the earth. After a certain height, after stratosphere or the atmosphere, there is no particles. It is completely a vacuum. But the radiations from the sun travels and reaches the earth in the form of electromagnetic waves. Here no medium is required. You take any solid body or liquid body or the gaseous body. All the bodies, all the fluids, all the solids have a tendency of radiating thermal energy, have a tendency of radiating the energy in the form of electromagnetic waves, and they absorbs from the neither body. When the bodies were separated in the space, and even when the vacuum exists between them, This type of heat transfer is called thermal radiation. Thermal radiation is a mode of heat transfer in which the energy transfer or the exchange of energy takes place between the two bodies or between the 2 points in the form of electromagnetic waves. Here there is no requirement of any molecules. The radiation heat exchange takes place even in the vacuum. Okay, this is what we discussed in the last class. The next concept is the laws which are applicable to the heat transfer. You studied zeroth law, first law, second law and third law in thermodynamics. Similarly, here in the heat transfer we are having some laws which states how the transfer of heat takes place in each mode. Fourier law of heat transfer, which is applicable for conduction, Newton's law of cooling, which is applicable for convection, Stefan Boltzmann law, which is applicable for radiation. Okay, the first law that we are discussing here in heat transfer is the Fourier law of heat transfer. Fourier law of heat transfer states that the rate of flow of heat through a simple homogeneous solid is directly proportional to the area of section at right angles to the direction of heat flow. The rate of flow of heat through a simple homogeneous is nothing but having uniform characteristics throughout its homogeneous, nothing but having uniform characteristics, is directly proportional. The rate of heat transfer which takes place through the solid is directly proportional to the area of the section. Area of the section which is at right angles. Right angle is nothing but which is at 90 degrees to the direction of heat flow. To the direction of heat flow and the change of temperature with respect, nothing but inversely proportional to the length of path of the heat flow. What it states is, here let us assume the heat is transferring across the slab from point 1 to point 2, from hot wall to the cold wall. Okay, this Fourier law of heat conduction is applicable only for one-dimensional cases. It states, it gives the amount of heat which is transferred only in one direction. It is not applicable for three-dimensional cases. Here let us assume the heat is transferring from left to the right side. The rate of heat transfer means the amount of heat which is transferred from left to right through this wall, through this solid material, is directly proportional. Here you can see the equation is the amount of heat Q. The rate of heat transfer is nothing but the amount of heat which is transferred through the material per second. The amount of heat which is transferred through an homogeneous solid is directly proportional to the cross-sectional area which is perpendicular to the direction of heat transfer. Perpendicular is nothing but which is at 90 degrees to the direction of heat transfer. This is not this area which is parallel to this direction. We need to consider the area which is perpendicular here. We need to consider the area which is perpendicular to this direction of heat transfer. The heat transfer, the rate of heat transfer through an homogeneous solid is directly proportional to the cross-sectional area which is perpendicular to the direction of heat transfer, and it is also directly proportional to the temperature difference across the solid means it is directly proportional to the temperature difference between which the heat transfer is taking place. Here the heat transfer is taking place between the temperatures T1 and T2. T1 is the higher temperature, T2 is the lower temperature, and the heat transfer is taking place from T1 to T2. A into T2 minus T1, because Fourier law states that it is directly proportional to the cross sectional area and also directly proportional to the temperature difference across the solid, and also it is inversely proportional to the length of heat flow. Here the length, the thickness of this slab is dx. Between 1 and 2 it is having the length dx, and it is inversely proportional to the length of heat flow. Q is directly proportional to the cross sectional area and temperature difference, and it is inversely proportional to the length of heat flow. We can write this equation in the form Q equals minus K into A into dt by dx, where K is the constant of proportionality constant known as thermal conductivity of the material. Here I have used the negative sign before the term K, which indicates that the temperature decreases in the direction of heat transfer. We know that the heat always flows from high temperature to the low temperature region. Here the negative sign indicates that the heat transfer, the temperature decreases in the direction of heat transfer in solids. Q equals minus K into A into dt by dx. Since the temperature decreases in the direction of heat transfer, and we know that dt is nothing but the temperature difference, final temperature minus initial temperature. Since T2 is always less than T1, T2 minus T1 divided by dx is always negative. Negative into this minus sign gives you the positive value. Therefore the heat transfer is always positive, although the temperature gradient dt by dx is negative. Therefore the equation becomes Q equals Ka into T1 minus T2 divided by dx, which is a positive value. Here in this equation Q gives the heat flow through a body or the solid body per unit time in watts. A is the surface area or the cross sectional area which is perpendicular to the heat transfer in meter square. Dt by dx is the temperature gradient. K is constant of proportionality, which is known as the thermal conductivity of the material. Some of the assumptions were made in stating this Fourier law. This conduction of the heat takes place under steady state condition. Steady state condition is nothing but there is no variation of temperature at a particular point with respect to time. That means T1, the temperature T1 and T2 remains the same with respect to time. That means whether you measure the temperature at 1 hour, at 2 p.m. or 3 p.m., whatever may be the time, the temperature doesn't vary. That is called steady condition. If the temperature varies with respect to time, then it is called unsteady condition or transient condition. Here in the Fourier law, for stating the term Fourier law, we assume that the conduction of the heat takes place under steady state condition, and the heat flow is unidirectional. I already said Fourier law is applicable only for one-dimensional cases. It gives the amount of heat which is transferring only in one direction. Actually the heat transfer takes place in all the directions, but it gives, the Fourier law gives the amount of heat which is transmitted only in one direction, and it also assumes that there is no internal heat generation. That means when the energy is made to flow through any body. Some amount of heat is generated within the body. Here we neglect the internal heat generation. And the fourth assumption which was made in the Fourier law of heat conduction was the material is homogeneous and isentropic. That means the properties of the material remain same throughout the body. It doesn't varies from one point of the body to another point of the body. It remains same throughout the body. Okay. The next concept is thermal conductivity of the material. From Fourier law, we are having the equation Q equals K into A into dt by dx. Rearranging that equation, we will get K equals, where K is the thermal notation for the thermal conductivity of the materials. K equals Q by A into dx by dt, where Q is the heat in watts, A is the area in meter square, dx is the length of the material in meter, and dt is the temperature in Kelvin. Meter get cancels, we left with watt per meter Kelvin or watt per meter degree Celsius. This is the unit of thermal conductivity of the material. Unit for thermal conductivity of the material is watt per meter Kelvin or watt per meter degree Celsius. And thermal conductivity of a material is defined as the amount of heat which is conducted through a body. Thermal conductivity of a material is defined as the amount of heat which is transferred, which is conducted, because it is applicable for conduction. Thermal conductivity of a material is defined as the amount of heat which is conducted, which is transferred through a body, through a solid body, through a body which is having unit area and unit thickness in unit time, and when the temperature difference between the phases causing the heat flow is unity. That means it is the amount of heat which is conducted through a body which is having unit cross sectional area, means 1 meter square, area of 1 meter square, unit thickness, nothing but the thickness of the material is 1 meter in unit time, means per second. It is the amount of heat which is conducted through a body having unit cross sectional area, unit thickness, that means 1 meter square of area, 1 meter of thickness in unit time, nothing but in 1 second. And when the temperature difference between the phases, between the 2 points across which the heat transfer taking place is also unity, that means having a temperature of 1 degree Celsius. That means it is the amount of heat which is transferred through a material of having unit cross sectional area, unit thickness in unit time, and when the temperature difference between the phases causing heat flow is also 1 degree Celsius. Okay. The materials with higher thermal conductivities are good conductors of heat. That means if a material is having higher thermal conductivity, it allows the maximum amount of heat to pass through it. Okay, the materials with higher thermal conductivities are good conductors of heat, whereas the materials with low thermal conductivities are good thermal insulators. High thermal conductivity is nothing but they allow the heat to flow through it. Thermal conductivity a property of the material, and it depends on the material structure, what is the moisture content of the material, what is the density of the material. With variation in the material structure, with variation in the moisture content of the material, with variation in the density of the material, the thermal conductivity of the material also varies. Thermal conductivity of most metal decreases with increase in temperature. That means at lower temperatures the metals allows maximum heat to flow through it. As the temperature increases, the thermal conductivity decreases. That means they allow the amount of heat, the less amount of heat to flow through it. The thermal conductivity of most metals decreases with increase in temperature, except for aluminum and uranium. I already said it is depends on material structure, moisture content and density of the material. For aluminum and uranium, with increase in temperature, the thermal conductivity of the material also increases. But for other metals, it may be gold, it may be silver, it may be iron, the thermal conductivity of the material decreases. Similarly in the liquids also, but in the liquids it reverses. With increase in temperature, the thermal conductivity of the material decreases with temperature. But in water, due to decrease in, but it reverses in water. Because the increase in temperature, the density of the water decreases. Okay. The next concept is Newton's law of cooling, which is applicable for convection heat transfer. It states that the rate of heat transfer for convection, the rate of heat transfer by convection between a surface and a fluid, between a surface and a fluid is directly proportional to the surface area which is exposed to the heat transfer and the temperature between fluid and the surface. That means here the amount of heat transfer which takes place by convection, between a solid surface and a liquid is directly proportional to the surface area A of the solid surface. Surface area A of the solid surface, and it is also directly proportional to the temperature difference between the surface and the fluid. Here T suffix S is the temperature of the surface which is exposed to the atmospheric air or the fluid, whatever it may be, and Tf is the temperature of the fluid. T suffix F is the temperature of the fluid, and T suffix S is the temperature of the surface which is exposed to the fluid. Q is directly proportional to the surface area A and the temperature difference between the surface and the fluid. We can write this equation as H into A into T suffix S into T suffix F, where H is the constant of proportionality called film heat transfer coefficient or convective heat transfer coefficient. Similar to the thermal conductivity in the Fourier law, here also H is the film heat transfer coefficient or convective heat transfer coefficient. Newton's law of cooling is applicable for convection heat transfer, which states that the rate of heat transfer by convection between a surface and a fluid is directly proportional to the surface area of the solid which is exposed to the heat transfer and the temperature between the fluid and the surface. Okay, this is what the Newton's law of cooling states. Newton's law of cooling states that the rate of heat transfer for convection between a surface and a fluid is directly proportional to the surface area exposed to the heat transfer and the temperature difference between the fluid and surface. Here the equation can be rearranged in the form H is equals Q by A into 1 by Ts minus Tf, where the unit of Q, the heat transfer, is watt, area is meter square, and the temperature is Kelvin. Therefore, the unit of heat transfer coefficient or film heat transfer coefficient or convective heat transfer coefficient, or it is simply called heat transfer coefficient, is watt per meter square degree Celsius or watt per meter square Kelvin. And this film heat transfer coefficient or the heat transfer coefficient denoted by the letters small h is defined as the amount of heat which is transmitted for a unit temperature difference between the fluid and unit area of the surface in unit time. Heat transfer coefficient is defined as the amount of heat which is transferred between a surface having unit cross-sectional area and a fluid whose temperature difference is also unity. That means the temperature difference between the surface and the fluid is 1 degree Celsius, and when the surface which is exposed to the unit heat transfer is 1 meter, it is called film heat transfer coefficient. Film heat transfer coefficient gives the amount of heat which is exchanged between the surface and the fluid having unit temperature difference, and the area which is exposed to the heat transfer is unity in unit time. The value of heat transfer coefficient depends on what is the nature, geometry of the surface which is exposed to the heat transfer, whether it is a sphere, whether it is a cylinder, whether it is a plane wall. Heat transfer coefficient varies with the geometry of the surface, and it also varies with the nature of the fluid, whether it is a gas, whether it is a liquid, whether it is water, or whatever it may be. It varies with the nature of the fluid and it varies with the geometry of the surface. Okay, this is all about Newton's law of cooling. The third law which is useful in heat transfer is Stefan Boltzmann law of radiation heat transfer. Next law is Stefan Boltzmann law of radiation heat transfer. We already studied that radiation heat transfer is the mode of heat transfer which takes place even in the vacuum in the form of electromagnetic radiation. A heated body placed in the presence of cooling surroundings but having no physical contact with them is observed to lose thermal energy due to thermal radiation. The rate of emission independent of the material, and it depends only on temperature. Okay, any body you place in a cooling environment, it loses its heat, and the amount of heat which is emitted by the body in the form of radiation, the amount of heat which it loses in the form of radiation, it is independent of the material, and it only depends on the temperature of the body. Okay, this is what the Stefan Boltzmann law states. Stefan Boltzmann law states that the thermal radiation from the black body A black body is one which absorbs all the radiation falling on it. Stephen Boltzmann law states that the thermal radiation from the black body, a black body is one which absorbs all the incident radiation falling on it, is proportional. The amount of radiation emitted by a black body is proportional to the fourth power of the absolute temperature of the surface. That means the amount of radiation emitted by a black body is directly proportional to the temperature, fourth power of the temperature, and the surface area which is exposed to the heat transfer. The radiation heat transfer only depends on the two factors: the temperature of the body, the fourth power of temperature of the body, and the surface area which is exposed to the heat transfer. Q is directly proportional to the surface area A and fourth power of the temperature. We can write this equation: Q equals sigma into A into T to the power of 4, where sigma is a constant of proportionality called Stephen Boltzmann constant, whose value remains constant whatever for a black body. Its value is 5.67 into 10 to the power of minus 8 watt per meter square Kelvin to the power of 4. The value of Stephen Boltzmann constant remains constant and its value is 5.67 into 10 to the power of minus 8 watt per meter square Kelvin to the power 4. Sigma can be rearranged. The equation can be rearranged as sigma equals Q by A into T to the power of 4, and therefore its V unit becomes watt per meter square Kelvin to the power of 4. That's all for today. We will discuss in detail these equations, these laws in the next class. Thank you.